Hello, welcome back to our discussion on nuclear chemistry. Early on, we discussed about the different types of nuclear reaction. And we introduced the nuclear reaction by considering the effects of high energy cosmic ray entering the atmosphere. At this point, you are aware on the notion of nuclear technology that both in weapon and power plants that can be used to release tremendous amount of energy. But you will ask, where does this energy come from? And why are the energies of nuclear reactions so much larger than in an ordinary chemical reaction? To consider this question, we will need to turn our attention to nuclei and the forces that holds them together. And before we go in detail on that, let us recall your theory on the atomic structure based on the Rutherford model of the atoms. Rutherford, in his experiment, after bombardment alpha ray through a gold foil, realized that there is a tiny space in an entire atom that is very tiny and massive. It is positively charged. This theory of Rutherford was based on the amount of deflection of alpha ray when he bombarded a gold foil. Only one out of the 20,000 alpha ray deflected at a large angle. He concluded that that must be a positively charged particle within an atom, which is mostly empty space, and it is where the most of the mass of the atom is concentrated. And he named it the nucleus, being the center of an atom. Comparing that, in our previous discussion, we discussed the how small is the nucleus with the entire volume of an atom. Now, considering that size of the nucleus compared to the entire volume of the atom, and the charges in the nucleus being composed of proton and neutron, proton positively charged, neutron being neutral. So, and based on the Coulomb law that like charges repel each other, so you will wonder what forces that holds together these positively charged in a very tiny space in the entire volume of an atom. The answer to this is contained in the Einstein famous equation, which describes the interconversion of mass and energy, and we call it the binding energy. The nuclear binding energy is the amount of energy required to break apart a nucleus into its component nucleons. The conversion of mass defect into energy can be calculated using the Einstein equation, E is equal to mc squared, where E is the amount of energy and m is the mass and c is the speed of light, which is equal to 2.99792 times 10 to the 8 meter per second. Sometimes this is round off to 3 times 10 to the 8 meter per second. So we can replace the E for Einstein by E sub B, being the nuclear binding energy. And we have the mass here by the mass defect, the change in mass. And we have the C squared. So the nuclear binding energy can be an expression of E sub B is equal to the mass defect times the square of the speed of light, where E sub B is the nuclear binding energy, the delta M is the mass defect, and the mass defect can be computed by taking the difference between the mass calculated minus the mass experimental, where we can say that the mass calculated is the theoretical mass of the nuclei. And this is referring to the mass of the proton, the total mass of the proton in the nuclei, by multiplying it by the total number of proton in the nuclei, which is referred as the atomic number as well, and the total number of neutron times the mass of the neutron. Again, from the earlier discussion, you can compute the number of neutron by deducting the number of proton from the mass number. Okay. And we're given here the value for the mass of the proton, which is equal also the mass of an hydrogen atom, which has a 1 proton and 0 neutron. Okay. Okay, we have the mass is 1.007825 atomic mass unit, and a neutron has a mass of 1.008665 atomic mass unit. And 1 atomic mass unit is a very useful conversion later. 1 atomic mass unit is equal to 1.66054 times 10 to the negative 27 kilogram. And from Avogadro's number, from your general chemistry, a mole of a substance is equal to 6.022 times 10 to the 23rd atoms or particle per mole. Okay. So let us have an example on how to compute the binding energy of a nuclei. For our first example, we're asked to calculate the nuclear binding energy of lithium-7 nucleus if the experimentally observed mass of lithium-7 atom is 7.01600 atomic mass unit. And you're asked what is the nuclear binding energy of a mole of lithium. Okay? Since lithium-7 lithium has atomic number of 3, and that refers to the number of protons, which is the charge, the positive charge. And the mass of 7, the mass number 7. So 7 minus 3 would give you the number of neutron. Okay. So if you take the equation a while ago for the computation of the mass calculated or the theoretical mass of a nuclei, that is the number of proton times the mass of proton plus the number of neutron times the mass of neutron. Since we have 3 protons and 4 neutrons, we can substitute it here. Okay, we have 3 protons multiplied by the mass of proton, which is 1.0078225 atomic mass unit as given here. And we have 4 neutrons multiplied by the mass of neutron, 1.008665 atomic mass unit. Okay, and that will give you the mass calculated, 7.058135 atomic mass unit. Okay, to compute the mass defect, that is the difference between mass calculated minus the mass experimental of the nucleus. And this time we are given the mass of the lithium-7 atom. Okay, so we plug in the value. We have the calculated here and the given mass of lithium-7 atom, 7.01600 atomic mass unit. And that gives you a mass defect of 0.042135 atomic mass unit. This can be converted, the atomic mass, this is per nucleus. This value is per nucleus of lithium-7. Okay, we convert the atomic mass unit to kilogram. Okay, by this factor, that one atomic mass unit is 1.66054 times 10 to the negative 27 kilogram per atomic mass unit. So the atomic mass unit here, the mu will cancel out. That will give you the mass defect is 6.9967 times 10 to the negative 29 kilogram per nucleus of lithium-7. Okay, moving on for the equation using the Einstein equation for combined conversion of mass into energy. Okay, we have the mass defect into binding energy. We substitute that value that we obtained a while ago. And we have the constant for the speed of light. We square that. and that will give you a value of the binding energy 6.2883 times 10 to the negative 12 kilogram meter square second squared per nucleus of lithium. Since 1 joule is kilogram meter square per second, therefore this unit is joule per this is joule per nucleus of lithium 7. Okay, to compute for the binding energy per mole of lithium 7, we use the Avogadro's number. Since for every one atom of lithium 7, there is one nucleus, the common sense. And in 1 mole, according to Avogadro's, there are 6.022 times 10 to the 23rd atoms. The unit atoms cancel out. The atoms cancel out here. The nucleus cancel out. And that leaves you the unit joule per mole of lithium 7. Okay, and it is positive 12 because negative 12 here will multiply by this factor. This will give you a positive exponent to the 12. Okay, that is 1 mole of lithium. Now you ask what is the significance of this value? Okay, let us further elaborate the significance of that value. We can relate that to the chemical reaction that we have discussed in thermochemistry. Then we can ask how many liters of gasoline would have to undergo combustion to provide this equivalent binding energy of 1 mole of lithium 7. Okay. And how many times will it take an ordinary car to drive around the Earth equator, consuming the amount of gasoline that we have computed in part B, referring to the binding energy of 1 mole of lithium? To answer that question, what is the equivalent liters of gasoline that would have? We refer to your table for specific density and energy density of some fuels in your module number 3 on fuels. Okay, so from table 3.3, page 10 of module 3 on fuels. We have for gasoline, the energy density is in the U is equal to negative 33. That is an exothermic 867 megajoule per cubic meter. So that is the amount of heat released per cubic meter by gasoline. Okay, during combustion of 1 cubic meter. That is the amount of heat release. Okay. For part B, we can, since the binding energy, we can determine how many liters of gasoline will equate that much of energy, binding energy released by 1 mole of lithium. So we have liters of gasoline be equal to, divide that, 3.7868 times 10 to the 12 joule per mole of lithium 7. If this much is released, you have 33,867 times 10 to the mega is 6 joule per cubic meter. Okay. So the joule cancel out. So since a 1 cubic meter is 1,000 liter. say the cubic meter will cancel out. So this will give us, compute that, we have 111,814 liters of gasoline per mole of lithium 7. Okay, that is the number of liters of gasoline to combust to equate that per mole of lithium 7. Okay, now for letter C, how many times will it take an ordinary car to drive around the Earth equator, consuming the amount of gasoline in letter B? Okay, if you are referring to the Earth equator here, theoretically, an average circumference of the Earth at the equator is 40,075 kilometers. Okay, we'll use that value later. Let us proceed with this one. Now, in the discussion under fuels, the distance that can be covered by this much of gasoline, assuming that an ordinary car would run with 100 kilometer per 5 liters. So the distance, we can have one distance covered would be equal to 11,814 liters gasoline. Say an ordinary car will take 100 kilometer per 5 liters. So the liters will cancel out. That will cover a total distance of 'Okay. This is per mole. This is per mole of lithium 7. So this is the distance covered per mole of lithium 7. Okay. If you the binding energy per mole of lithium 7. So we are asked how many times will it take an ordinary car if that ordinary car will cover 100 kilometers per every 5 liters around the Earth equators. Okay, if the Earth has at the equator has a circumference of 40,075 kilometers. Okay, so we can have that. We can divide that by that circumference. So we have the number of times around Earth equator. If 2,236,277 kilometer can be covered if you have a binding energy per mole of lithium 7 and the Earth equator is the circumference rather of the Earth equator is 40,075 kilometer per round. Okay, that is around. Okay, so the kilometer will cancel out, so that will give you 55.8 rounds per mole of lithium 7. So that means you have approximately, you will have 56 times. Okay, you will go 56 times around Earth equator. That is equivalent, okay, when you use up this much of gasoline using our ordinary car, okay, which is this much of gasoline is equivalent to the binding energy of 1 mole of lithium 7. Okay, so that's how tremendous the amount of energy released by a 1 mole of lithium 7 alone. Okay, so if you recall that the energy released in an exothermic chemical reaction is typically in the order of hundreds of kilojoule per mole, but this one is a factor of 10 to the 12 joule per mole. Okay, thus it will take you 56 times to travel around the Earth equators to use up that energy using our ordinary car by burning an equivalent gasoline of that much at 111,814 liters. Okay. Okay, for the second example on nuclear binding energy, we're asked to calculate the mass defect and nuclear binding energy in the unit joule per nucleons and mega electron volt per nucleon of a nuclide of nickel 58, whose atomic mass or the experimental atomic mass of nickel 58 is 57.893 atomic mass unit. Okay, for our solution, we begin with determining the number of neutrons and protons. So nickel from the periodic table has an atomic number of 28. Okay, so 28 for nickel as the atomic number, and that refers to the number of proton 28. So the number of neutrons is 58 minus 28, that gives you 30. So if we plug in that number of protons and neutrons to this equation and multiply that number of particles to its respective mass, so proton is 28 multiplied by its atomic mass, which is 1.007825 atomic mass unit, and the neutron, we have 30 neutrons multiplied by its mass, which is 1.008665 atomic mass unit. Okay, computing that, that will give you a value of 58 and 479,000 atomic mass unit. Okay. That is the mass calculated. Since we're given here the experimental, so we can compute for the mass defect. That is the mass calculated, 58.479 atomic mass unit minus the experimental. Therefore, the mass defect is, the difference is 0.58 per nucleus of nickel 58. So if we convert that into kilogram, that one atomic mass unit is 1.66054 times 10 to the negative 27 kilogram. Okay, the mu will cancel out. That will give you a value. We multiply that correspondingly with, that gives you a value of 9.73 times 10 to the negative 28 kilogram per nucleus of nickel 58. Okay. Okay, to compute for the binding energy in the unit joule per nucleons. Okay, so we plug in the value of the mass defect in terms of kilogram. We have 9.73 times 10 to the negative 28 kilogram per nucleus of nickel 58. And we have the value for the speed of light, 2.99792 times 10 to the 8 meter per second, and we square that for c squared. Okay. So if we enter that value, that will give you the binding energy equal to 8.746 times 10 to the negative 11. 11 joule per nucleus of nickel 58. Okay, since nickel has for every one nucleus of nickel 58, it has 58 nucleons. That is the number of particles in the nucleus. Okay, 28 plus 30. That is 58 nucleons. So therefore, the binding energy in the unit joule, the nucleus will cancel out. That will give you 1.5 08 times 10 to the negative 12 joule per nucleon. Okay. Or approximately 1.51 times 10 to the negative 12 joule per nucleon of nickel 58. Okay, that is for the first unit in joule per nucleon. Okay, moving on, since the amount of energy produced in nuclear reaction is in electron volt or mega electron volt, hence the mass defect can be expressed as the binding energy using the direct relationship with atomic mass unit and electron volt and mega electron volt. This gives us one atomic mass unit is 931.5 times 10 to the 6 electron volt. We replace that factor. One atomic mass unit is equal to 931.5 mega electron volt. So we can express the binding energy in mega electron volt by converting the mass defect here to mega electron volt. So the mass defect per nucleus, you have 0.586 atomic mass unit per nucleus of nickel 58. Okay, so we can convert that. For every one atomic mass unit, that is equivalent to 931.5 mega electron volt. Okay, since for one nucleus of nickel 58 has also 58 nucleons. Again, the nucleons are the particle in the nucleus, which is the proton and the neutron. So we just add 28 and 30. That gives you 58 nucleons. So to compute for the binding energy in the unit mega electron volt, when the atomic mass unit cancel out, the nucleus cancel out, that leaves you mega electron volt per nucleon. So that value is 9.41 mega electron volt per nucleon of nickel 58. Okay, so that is being asked in the unit of mega electron volt. For joule per nucleon, this would be our answer. Okay, then still on the binding energy for the third number, it takes 360 kilojoule to keep a 100-watt light bulb burning for 1 hour. Assuming that the light bulb won't burn out, how many years could the energy of a mass defect of 1 mole of carbon-14, whose atomic mass is 14.003242 atomic mass unit, keep a 100-watt light bulb burning? Okay. So to answer the problem, we have to compute first the binding energy that will be the binding energy required to hold the nucleons of 1 mole of carbon 14. Okay, to start with, for our solution, okay, we have carbon 14. The atomic number of carbon is 6. Therefore, the number of proton is 6 and the number of neutron is 14 minus 6 is 8. So to compute for the first is we compute the mass calculated. Okay, that will give us proton, 6 proton times the mass of a proton, 1.007825 atomic mass unit, plus 8 times the mass of a neutron, that is 1.008665 atomic mass unit. That gives you the mass calculated is 14.11627 atomic mass unit. Next step is we determine the mass defect, which is mass calculated minus mass experimental, which is given here. So we have 14.116 27 atomic mass unit minus 14.003242 atomic mass unit. So the mass defect is 0.113028 atomic mass unit per nucleus of carbon 14. Okay. So if you convert that to kilogram, one atomic mass unit is 1.66054 times 10 to the negative 27 kilogram. So the atomic mass unit will cancel out. The mass defect therefore give you 1.877 times 10 to the negative 28. The unit is kilogram per nucleus of carbon 14. Okay. To convert that to binding energy, we have mass defect times c squared. So the binding energy is 1.687 times 10 to the negative 11, that is joule per nucleus of carbon 14. Since using the Avogadro's number, you have 6.022 times 10 to the 23rd nucleus per mole. So the nucleus cancel out. So the binding energy 1.016 times 10 to 13 joule per mole of carbon 14. So the next step is, with this much of energy, we're asked how long will a 100-watt light bulb keep on burning without burning out. So we can have it, the number of years the 100-watt light bulb will live without burning out is equal to 1.016 times 10 to the 13th joule per mole of carbon 14. Okay. And it consumes 360 times 10 to the third joule per hour. So the joule cancel out. Since we have in one day We have 24 hours, and in 1 year, you have 365 days, conservative without leap year. So the hour cancel out, the days they cancel out. That will give you the number of years. So that will give you 3,221 years per mole of carbon 14. Okay, this is the number of years that a 100 watt light bulb will lit, assuming that it won't burn out continuously. Okay, that would be the number of years. Since a light bulb will be busted only based on the number of times you click it. Assuming that once you open it, you don't turn it off anymore. This is the number of years that the energy of mass defect of 1 mole of carbon-14 will keep 100 watt light bulb burning, in the assumption that the light bulb won't burn out. Okay, from this example, we have seen that the amount of energy required to break apart a nucleus into its component nucleons is tremendously enough to light a light bulb, 100 light bulb, for 3,221 years without burning just a mole of carbon 14. And likewise, in the first example, we computed how many times we can go around the Earth equator by just breaking a nucleus of 1 mole lithium 7. Okay, we have 56 times around the Earth equator as a mole of lithium 7. After our calculations of binding energies of some nuclei, this can provide us with some added insight into nuclear stability. A convenient way to visualize this is through a plot of the binding energy per nucleon versus the mass number. We have here the binding energy on the y-axis versus the mass number on the x-axis. Okay, the plot shows that the binding energy per nucleons goes through a maximum here. This is the maximum, indicating that there is a region of maximum nuclear stability. The region is centered around iron 56, indicating that this is the most stable of the known nuclei. This plot suggests that two processes might produce greater stability. If two lighter nuclei here can be combined, this would result to a nucleus with greater stability here. Such process is called nuclear fusion, which we have discussed in the previous episode on the types of nuclear reaction. On the other hand, the heaviest nuclei here can split, resulting into two or more lighter nuclei. Okay. That might fall within this region of greatest stability. This is called nuclear fission. In the next episode, we will look at both processes in more detail, where we will discuss the energetics of nuclear reaction that involve nuclear fission or nuclear fusion. Okay, that's all for binding energy. Next, we will discuss the energetics of nuclear reaction.